Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So we meet again. Okay, I would like to continue beam analysis, beam with support settlement analysis. Okay, let's look at this exercise. Okay, this exercise actually I take from the class note, okay, that I have actually put into your class notebook. Okay, let's together watch this. Okay, watch this video until the end. Okay, so we will discuss these examples. Okay, let's look at this together. Okay, exercise number 2. Analyze continuous beam by the moment distribution. Analyze continuous beam means we need to calculate n moment. We need to calculate n moment. Okay, n moment or internal moments. Support B and C settled by 8 mm and 4 mm respectively. Okay, support B and C settled by 8 mm and 4 mm respectively. EI is given as 30,000 kilonewton meter square. Okay, next, the second question, sketch a shear force diagram and bending moment diagram. Okay, let's look at this together. Okay, so okay, here in this example, there are 1, 2, 3. 1, 1, 2, 3. Three join. Okay, 1, 2 join. A, B, and C. 3 join. So how many members? How many members? We have member AB, we have member AB, and we have member B, C. Okay, we have member AB. This is number 1, number 2, join number 2, join number 3. Okay, 3 join. Okay, 3 join. So we have 2 members. We have member AB and we have member B, member BC, AB and BC. Okay, so A is fixed, C is roller, So as usual, before we continue, before we can start distribute moment, we have to determine distribution factor, and distribution factor we can determine by a simple formula. It is K divided by total K. Okay, let's check what is the K value for AB and K value for BC. Okay, for AB, we will use K, which is equivalent to 4 EI. It is 4 EI. 4 EI divided by length is 4 meter. Okay, that is for K because N is fixed, for N fixed. And for BC, okay, K for BC, we will use 3 EI because NC is roller. Okay, this is 3 EI. 3 EI divided by length is 6 meter. Length is 6 meter. So from this we can calculate distribution factor. Distribution factor for AB we will get as 0. Okay, distribution factor as 0 because fixed for fixed N, distribution factor is equal to 0, and for roller or pin N, distribution is equal to 1. Okay, equivalent to 1. So we have two value here. For BA and as well as BC. Okay, BA as well as BC. It is K divided by total K. Means that if we want to calculate this value, okay, which is belong to BA, means that it is, okay, this one we simplify, we get EI. This one we simplify, we get 0.5 EI. Okay, so for EI will be cancelled. That is why we don't need to substitute EI value whenever we calculate stiffness. Okay, whenever we calculate stiffness factor. Okay, it is 1 divided by 1.5 EI. EI over EI cancel for distribution factor. It is 1 divided by 1.5. Okay, it is 1 divided by 1.5. It is 0.667. Okay, it is 0.667. Okay, so another one is 0.333. Okay, because the total of this must equal back to 1. total equal to 1. So this is actually distribution factor. So all this we will transform into table, because we will calculate in the table form, and moment in the table form. Okay. So next one we want to now calculate FEM. Okay, in this case there are two FEM. So FEM is actually FEM, okay, can be divided into two, okay, two condition. Number one is due to external loading. Number two is due to delta. Okay, and delta for beam we refer to support settlement. External loading and support settlement. And both of these we can calculate value, because external loading is given in question, support settlement also given in question. So we can actually total these two and solve using one table. Okay, we will now calculate FEM due to internal loading and due to support settlement, and then we combine together before we put into the table. Okay, due to external loading. Okay, let's see. For member AB, it is 4 meter length and 240 kilonewton point load subjected at the center. So we use PL over 8 for AB. This is for AB. Okay, for AB, we have this. This is 240. Okay, total length is 4 meter. Okay, it is 2. Okay, so the moment is acting in this direction because of the behavior. Okay, because of the behavior, and the formula is PL over 8. The formula is PL over 8. One negative, one positive. Okay, PL over 8. L is 4 meter. L is 4 meter, so this is equal to 240 times L 4 meter divided by 8. Okay, divided by 8, so we get 120. We get 120. So this is 120. This is 120. Okay, this is 120 for AB. Okay, for AB. For AB, due to support settlement, this is due to this is due to external loading. Okay, now for member AB. Okay, for member BC first. Okay, for member BC, again still under external loading. For BC, okay, for BC we have to assume that, okay, internal always fixed, so we apply back the value, the W value. It is 40. It is 40. WL squared. L is 6. 40 and 6. This is 40. This is 6. So the moment acting in these two direction, both opposite condition. So it is WL squared over 12. It is WL squared over 12. Okay. It is W is 40. L is 6. WL squared over 12. So we get 120 also. 120. So the value is 120. Okay, the value here is 120. This is also 120. This is also 120. And all this is actually due to external loading. Okay, external loading. Okay, now we want to move to number 2. We want to move to this. Okay, we want to move to this. This is due to support settlement. So how we are going to do this? Okay, so we have to start with draw the free body diagram. Okay, draw the free body diagram. Okay, let's look at together the diagram. Okay, the free body diagram is like this. So we only have two members, A, B, and BC. So here is the member. Okay, the beam. Okay, here is the beam. So this is A, B, and C. A, B, and C. AB is 4 meter length. BC is 6 meter length. Okay. Okay, let's look at back to the question. B and C settle respectively 8 mm and 4 mm. B and C settle means that B and C move to new position 8 and 4. 8 first. Okay, 8 and 4. So at B, here is B 8 and C is 4. Okay, 8 and 4. So what we need to do is to identify displacement to identify fixed end moment due to delta, due to support settlement. So what we need to remember is always find where is the triangular. Okay, always find where is the triangular in the triangular. Okay, so we have to join A to new B position. Okay, to new B position. Okay, and length of this is 8 mm. 8 mm. So it is 0.008. This one is 0.008. And then at C it is 0.004. Okay, it's like this. Okay, 0.004. Okay, as I mentioned, always find where is the triangular. Always find where is the triangular. So mark the triangular. Okay, we have to mark the triangular. Okay. Okay, for delta at C is 0.004. This one is 0.004. Okay, as I mentioned just now, always find where is the triangular. Where is the triangular? So for AB, okay, for AB, this is the triangular. Okay, and for BC, it is, okay, it is this area. Okay, the yellow and the green. Okay, because we want to find the triangular. Because of the formula, we draw like this. We draw like this because of the formula. Okay, because the formula as given in the textbook. Okay, in the back page of the textbook. Okay, due to loading. Okay, the behavior is opposite. Okay, but due to settlement. Okay, due to settlement. Okay, this is actually the formula. Okay, so from the formula, this is L. This is L. Okay, this triangular, okay, must have perpendicular section. Perpendicular. Okay, and then the delta is actually here. This is the delta. Means that this is delta which is equal to 0.008. And length for this is 4 meter. 4 meter. Okay, for this AB, for this AB, okay, for this AB, okay, mark the angle from original position. Always remember, as I always repeat, okay, as I always repeat, okay, we have to mark the angle from original position. Original beam is horizontal. Original beam is horizontal. So we need to mark, okay, we need to mark the angle rotation. Okay, it rotates. How it rotates from original position to new position. Okay, so by looking at the triangular, okay, based on the formula, the angle is this. Okay, the angle. So this angle, okay, is called as chord rotation. Okay, the symbol is called rotation, and we call this as angle. Okay, angle. So this angle, when it is positive, okay, FEM will be negative. Okay, because of behavior. This is behavior. This is behavior. Because of behavior. And between delta and between FEM is opposite condition. Just remember this condition. Okay. So what about BC? What about BC? So for BC, the triangular, okay, the distance of the triangular, the distance of the vertical length, okay, from the lowest position, okay, so it is like this. Triangular, okay, like this. Okay, it is like this. Okay. Okay, this is like this. Okay, so this is B and C. Okay, of course B and C has support. Fixed end. Fixed end. Okay, fixed end. Okay, so perpendicular. Perpendicular. So this is 6 meter length. The length is 6 meter. Okay, mark the angle from original. From original, remember this is original. Original position. Original position. This is original position. Okay, so the angle, okay, now we want to mark the angle. The angle, okay, it rotate counterclockwise. It rotate counterclockwise. And one more thing that I want to highlight is because this is triangular and we actually apply what we already learned in school, okay, especially in mathematics. So based on this condition we have like this. We have like this. From original, from original, from original, so we can conclude that this, okay, the angle for BC, the angle, okay, we can conclude as this. Okay, angle is counterclockwise, FEM clockwise, FEM clockwise. Okay, so what is the formula that we are going to use? Okay, so for support settlement or for delta, the formula is very simple. It is equal to 6. It is 6 EI delta over L squared. It is quite straightforward and simple. And this is for both end fixed. This is for both end fixed. And we have another formula by considering one end roller or one end pin, so we can use 3 EI for that one. 3 EI delta over L squared. Okay, so this is for pin end. Pin or roller end. Okay? Okay, and the sign will be depend on the behavior. Okay, will be depend on the behavior. For example, for FEMAB, okay, for FEMAB, FEMAB equal to FEMBA equal to, okay, let's go back to the triangular AB. The triangular AB, okay, the angle is positive, FEM must be negative. So we put negative, so that when we calculate value, we get negative. We put negative. So this is 6, okay, times 30,000. 30,000, 6 EI delta is 0.008. Okay, 0.008. Okay, divide by L squared. L squared for AB is 4 meter, 4 square is 16. Okay, now we get FEM for AB and BA. For AB and BA, and sign is also equal. Okay, it is 6 EI delta, 6 EI delta over L squared. Okay, so we get negative value. So what is the answer? What is the answer? So we get 6 times 30,000 times 0.008. 0.008 divided by 16. So we get 90 here. 90 kilonewton. 90 kilonewton. Okay? FEMAB and FEMBA. So both this one, and fix. And fix for AB. For AB. Okay, now we want to move to FEM for BC. FEM for BC, this is equal to FEM for CB. Okay, so look at back to the diagram, because we want to mark the where is it? Okay, the delta. Mark the delta. So it is okay, FEM. Okay, mark the sign. Sorry, mark the sign. FEM, BC and CB. Okay, FEM is positive. FEM is positive here. FEM is positive. Okay, FEM is positive, so we put positive. Okay, so I want to use both and fix. Assume that both and fix, so we can apply 6 EI, 6 EI, 6 EI delta over L squared. Over L squared. Okay, and this will be equal to positive 6 times 30,000. Okay, times 0.004, because it is 4 and 8. It is 4 and 8 divided by, okay, it is 6 meters, 6 square is 36. 36. So we get this as 6 times 30,000 times 0.004 divided by 36. So we get 20. We get positive 20 kilonewton meter. Okay? Okay, now all this I want to combine. So combine FEM. Combine FEM. Okay, combine FEM. Okay, combine FEM. So we get, okay, what we get. So we have, okay, we have FEM for AB, for BC. Okay, this is due to external loading. This is due to delta. Okay, we want to find the total. We want to find the total moment. total fixed end moment, total fixed end moment, okay. So for AB, for due to loading AB we get 120. Okay, AB we get 120. AB, 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 BA, AB, BA, BC, CB. Okay, okay. So AB is negative 120. Okay, BA is positive 120. Okay, BC is 120 as well, negative 120 and 120. Okay, and for the delta, okay, so we use ABBA is negative 90. So we get negative 90 here, negative 90. Okay, negative 90. And BCCD is equal to 20. It is positive 20. 20. It is 20. Okay, so in total we get 120, 120, 220, 210. So this one is negative. Okay, and this one is positive 30. Okay, this one is negative 100 and 140. Okay, so this is actually the fixed end moment that we need to put into the table. Okay, into the table. So, okay, all is given as this. So this is the same value. Okay, same value here, same to what I have actually shown to you previously just now. Okay. Okay, so let's look at this table together. So we have AB, we have AB, BA, BC, CB. Remember, when we have only two members, okay, the process in the table will be short. Two or one cycle or two cycle will be enough. Okay, so it is 0 fixed end. Remember, fixed end. Okay, this 2 is equal to 1. This 2 is equal to 1. Okay, 0.67 plus 0.333 equal to 1. Distribution factor for pin, whether it is end pin or roller or the internal. Okay, internal is also 1. Okay, and this is 1 because of pin. This is 0 because of fix. Okay, that's why we get 1 here. Okay, so we put FEM, combine FEM, negative 210, positive 30, negative 100, and positive 140. Okay, so we need to distribute. Okay, we need to distribute. Balance here representing distribution. It is the same thing. Okay, distribution. As usual, so we find the total moment. Total moment. Okay, the total moment is, okay, this one. Okay, total moment is 30 and negative 100, we get 70. So this 70, when we time with 0.67, we get 46.9. Okay, and then 70, negative 70 again, negative 70, we time with 0.33. Okay, 70, negative 70, Okay, not negative. It is positive. Positive 70 times with 0.33, we get this. Okay, we must check 1, 2, 3, 4. Total these two must be equal to 0. Total these two must be equal to 0 because MB is equal to 0 because of internal condition, internal support condition, as well as the roller. Okay, that is located at B position. Okay, so and okay, for CB, it is 140. It is 140 here, 140. We times with 1. Okay, that is why we get negative 140. So total these two produce 0. Total 140 minus 140, we produce 0. Okay, so for carryover, we can carry to A because A is fixed, but we can't carry to C because C, the factor is 0. So here, the factor, carry over factor equivalent to 0. Okay, carry over factor equivalent to, 0 here, 1 here. Sorry. Okay, carry over factor, this is 0.5 and 0. 0.5 and 0. And fixed or internal support, we use 0.5, and roller and pin, we use 0. Okay, so that is why we can see clearly that, okay, 46.9. Okay, we time with factor, we get 23.45. We get 23.45, and there is no value here. This one is 0 because the factor is 0. Okay, next step is repeat distribution. Balance or distribution, doesn't matter, can be done both. Okay, choose either one. Okay, okay, now we want to distribute. We want to distribute. Okay, so the value is 70. We get from this. The value is 70. We get from this. It is negative. A joint moment is positive. So positive. This 70 we times with 0.67. We get this 46.9 and 23.10. Okay, then we repeat again the step carry over. So we carry the value 46.9, divide, we get 23.45, and 23.1, when we divide, the factor is 0. That is why we remain as 0. And then at this condition, what we can see is there is no value here. What does it mean? No moment to distribute. Okay, when there is no moment to distribute, means that it is the end of process. Okay, so total, what is total? Total means end moment. Total means end moment. Okay, we calculate start from which one? Start from this until this. Okay, so we get like this. Okay, we get like this. Okay, so the total moment, so we get here, we get this one equivalent to 0. So it is correct. Okay, and then total 1 and 2 must equal to 0. Clear. And moment at A must have value because it is fixed end. Then by using this, we can actually sketch, okay, the shape of the diagram. Okay, so this one is negative. So if we have negative, so for example, if we have this, okay, 1 and 2. Okay, it is negative. Negative, negative. Okay, second one, negative 0. Negative 0. Okay, so by looking, by drawing this, we can actually identify, okay, the first position will be here, the second position will be here, and then move to point load position, something here, okay, and then the last value must be 0. So we just join this dot. Okay, so this one. Okay, now I am drawing the bending moment diagram that we get directly from the table. Okay. And another one, it is UDL. So the first point will be 0 point. Okay, it move to okay, the last, sorry. This one is not the point. Okay, this one is not, because the last will be this, somewhere here. Because from the arrow that we get, it is negative, negative, like this. Okay, so this will be the bending moment diagram. Okay, like this. Okay, so we get this as positive, this is negative. What is the value? The value we take from table 163, negative 163. Here is 163. Okay, and 124, negative 124. So this is 124. Okay, 124. Okay, and then last one, it is positive. It should be one negative, one positive. We have to check back. So this one is positive actually. Positive. This one should be positive. Okay, positive value actually. Positive. So positive. So it is negative positive. It is negative positive. So the arrow should be like this. So the point should be at the bottom like this. And then this is the last point. Then we put ruler. So we take as this. Okay. So this is the right one based on the arrow. So 142 is located here. 142. Okay, this is BMD. This is BMD. Okay, BMD. So positive, negative. Okay, move to this. Okay. So it is negative. It is negative. So negative is in this direction. Okay, of course for UDL. Okay, for UDL, so the last point is 0 because of the roller. It is negative. It is negative, so means that the point is located somewhere here. Okay, so like this. And then the basically for UDL we get like this. And this maximum moment, okay, this is called as maximum moment, max moment. And the value we can only determine by using shear force diagram. Shear force diagram. Determine this value. Determine maximum moment using shear force diagram. Okay. So finally we get this. Okay. So the value is 118. Okay, the value is 118 here. So we get from shear force diagram easily. Okay. So I think that's all for this example. Actually, frame and beam analysis using moment distribution method. Okay, the process is actually straightforward. Okay, except the fixed end moment that when we analyze, we have to understand the behavior. Okay, the behavior of the beam. Okay, so FEM only, we have to consider at FEM. K same, distribution factor same. So for distribution factor, we have to use the formula given uh, by considering external loading and support settlement. Okay, so I hope this will help you to understand. And in next video, I will cover beam. Okay, with support settlement with 3 element or 3 members. Okay, so that's all for this session. Thank you very much for staying until the end of this. So hopefully this will help you to understand more in order for you to do your summative 1.2. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.